Welcome to lesson 43. We're talking compound inequalities. What's an inequality? That's an inequality. That's an inequality. Why is it called an inequality? It looks a lot like an equation, right? Except equations have an equal sign. That's not an equal sign, so we call it an inequality, which means not equal. It's a less than, right? And by the way, make sure you remember how this thing works. That's a less than symbol because this is less than this. Get it? If you flip the symbol around, it's a greater than symbol because this is bigger than this. The arrow points at the small one, or what a lot of people like to say is the mouth eats the bigger one. Here's like a mouth. It's got teeth and whatever. The mouth eats the bigger one. There, the bigger one's over here. I'm going to eat it. I'm going to put my mouth that way. Whatever works for you. I always think of it as, the little pointy side points at the little number. So anyway, that says 2x plus 8 is less than 12. That says 8 minus 2x is less than or equal to 12. Okay, and let's erase some stuff and start working on this stuff. Okay, so that's all we mean by an inequality. The compound part of inequality means we're gonna end up considering like two at a time or something. That's what. But before we do compound, let's just do some standard straight inequalities. So we're gonna do some linear standard one at a time linear inequalities. By the way, what does this linear mean? It's a good habit when you're playing around with math is to understand what the words are doing there. Like why do they have to say linear inequalities? Well, we're saying linear inequalities. What linear means is x is not squared or cubed or any other weird exponent or square rooted, or it's not in the denominator or anything like that. It's just a standard x to the 1. That's what we mean by linear equations and inequalities. Linear. We call it linear because if you were to take y equals 2x plus 8 and make a graph, it would come out as a straight line. That's where the word comes from. But we're saying linear because we don't want any exponents. What I'm doing here is not going to work if you have things like x squared plus whatever. Okay, these methods don't work so well. So we're just going to ignore those and not worry about those today. Okay, so linear inequalities is what we're doing. Now here's the big point. How do you solve a linear inequality? You solve a linear inequality in the same way as you do a normal linear equation, with one big exception. If you multiply or divide both sides by a negative, it reverses the direction of the symbol. If you multiply or divide, those are the only two things you have to worry about. If you multiply or divide both sides by a negative, then it reverses the direction of the inequality symbol. Now I can prove to you very quickly that this all works. Like, let's start with something like 5 less than 6. That's true. What happens if I multiply both sides by a positive 2? Well, that's a 10, that's a 12. That works. Multiplying both sides by a positive 2 didn't matter. Notice you can add stuff too. Like let's add 8. I don't know, just to make up a number. I'm adding 8 here. So of course that didn't make any, it's still true. It's still true. But now watch what happens if I divide by a negative 2 on both sides. So this is fitting the pattern here. We are dividing by a negative. It's supposed to switch the symbol around. 18 divided by negative 2 is a negative 9. 20 divided by negative 2 is a negative 10. And which is smaller, negative 9 or negative 10? Negative 10 is smaller, right? Because if you put it on a number line, negative 10 is to the left. That's smaller going this way. That's smaller. So notice what just happened there. I divided by a negative. That had to switch around. It had to change directions, okay? And hopefully you believe now why that must happen. So that's the one thing that's going to be different when we're solving these inequality things, these linear, I should say, inequality things. So with that by way of setup, here we go. Let's solve this one over here. Let's subtract 8 on both sides, right? That's kind of what you would do, isn't it? You'd subtract 8 on both sides because you're trying to get the x term by itself. 12 minus 8 is 4. First you get the x term by alone. Once you've got the x term alone, you say, well, I want an x, not a 2x. This is times 2x, so the way you undo the times 2 is you divide by 2. I always think of it as I want to cancel the 2 off. So you divide both sides by 2, and now x is less than 4 over 2 is 2. Okay? I never divided by a negative, so I don't have to switch anything around. I'm fine. So that basically solves this inequality. It works for all numbers less than 2. If you want, you can try some real quick. Yeah, you're saying that if I try a 1, it'll work? Well, let's see. 2 times 1 is 2. 2 plus 8 is 10. And yes, 10 is less than 12. Yeah, you're right. It worked. So you're saying that if I use something bigger than a 2, like a 5, that it won't work? Well, let's try this again. Put a 5 up here. 2 times 5 is 10. 10 plus 8 is 18. That's not less than 12. And you're right. The 1 did work. The 5, it works. You can always check yourself this way real quick like. Now, often what we like to do is, I mean, you've kind of answered the question, but often what we like to do is you might make a little map on the number line. So just kind of draw your number line. So it starts at negative infinity over there. It ends at positive infinity over there. Doesn't actually end, but it goes towards positive infinity over there. 2 is some number in the middle somewhere. So it just kind of comes sort of in the middle somewhere. And notice I'm using an open circle. And it's an open circle because it's a strict less than. Not less than or equal to, but less than. So you don't include 2. What you include is everything less than 2. And so what we tend to do is we tend to darken the number line over here. Maybe make that arrow a little bit bigger so we can see. So there's all your solutions. It's all the numbers that are less than, not equal to, but less than 2. Okay, cool. We'll come back to this number line thing in a minute. Now let's go over to this other inequality and solve this one. So I want to get the x term by itself. The first thing I want to do is I want to subtract 8 on both sides. So I've got a negative 2x. Remember that negative is still there. Negative 2x less than or equal to that 12 minus 8 is a 4. Okay, this is the part where I want to cancel a negative 2 on both sides. So the negative 2's cancel. That's an x. And then remember, I just divided by a negative. That has to flip around the other way. And 4 divided by negative 2 is negative 2. Okay, so that's the big thing. When you divide by a negative or multiply by a negative, you need to flip that direction. It's not a less than anymore. It's a greater than. Just flip the way it's pointing. So there's the solution of the one on the right. Now if I were to make a map of this one, get yourself a nice number line going. Negative infinity is always heads to the left. Heading to the right is positive infinity. Negative 2 is in the middle somewhere. Now this time, because it says less than or equal to, I'm doing a solid dot, and I made it really big to really emphasize that's a solid dot. That is not an open circle. Now, things that are bigger than negative 2 are on this side, so I'm going to sort of try to darken that side of the number line in. Okay, cool. Okay, so now that we've got our solution here and our solution here, and we've got our map of our solution and our map of our solution, I need to show you something called interval notation, because this is how we're going to be expressing our answers. Interval notation. It's important to learn it. We might as well just learn it now. Interval notation it's kind of a nice way of taking this picture and turning it into a little statement. You say, okay, what's the interval? An interval means, between here and here is an interval, right? So what's the interval? What's the interval that contains all the solutions? It's from here to here. It's everything from negative infinity up to 2. Now we don't include 2, so the round parentheses says don't include the end point. The end point is 2. Don't include the 2. And of course, you can't include negative infinity. It's not even a number. It's just a direction. It's a notion. It's a go that way and don't stop. So you can never get there if you're not stopping. So it's also a round parenthesis. Infinity always gets a round parentheses, put it that way, and negative infinity. So anyway, that's our interval notation. Doesn't it look cool? That's our official way to write this answer. How would you write this one with interval notation? Well, you've got negative 2 going to infinity. Right? And we do include the negative 2. That's what the solid dot was telling us. And so we use a square bracket. So the square bracket says do include the end point. The end point here is a -2. The border, if you will, is a -2. We include the -2 in our set of solutions, so we use the square bracket. Again, infinity, you cannot include infinity. It's not a number. You never get there. Infinity has to have a round parentheses. But there, lo and behold, this is called interval notation. And in the short term, this is important to you because your homework assignment, you have to give all your answers in interval notation. So we'll be playing with this some more in the course of this lecture. But one point to make about interval notation is notice we always go left to right when we're writing these intervals. In other words, reading like you're reading the number line, like you're reading a book, from here to here, from -infinity to 2. You would never, ever, 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 ever write that. That's backwards. That's bad. That's bad for you. That's wrong is what it is. Over here, reading the solutions off the number line, you start here and you read to the right. And so we start at -2 and we read up to infinity, okay? You would never, ever, 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 ever write this. You don't do it because that's backwards, okay? Don't write it backwards. Always go left to right like you're reading a book, okay? Please be careful about that. But that said, I think we can start handling some compound inequalities here. Compound inequalities come in two types. There's the intersections, which basically use the word and. It's where you have two inequalities and you want them both simultaneously satisfied. And that's actually what it's saying up here. And then there's going to be another kind where it's like we don't need them both. We just need one of them. Either one is fine. Or they're called unions. But anyway, let's focus on these intersections. Usually people like the intersections better, so we'll do those first. So, first type of compound inequality is an intersection. We have these two inequalities that we're considering together like a system. We're considering them together like a system. We want all numbers, all x's, that solve this and this simultaneously. When you want one inequality and another to be simultaneously satisfied, if that's what you're looking for, you're basically looking for where do the solutions overlap. Kind of like if my solution was 5 and 6 and my solution was 6 and 7, the answer to both would be a 6 because a 6 is in both. Okay, that's what I mean by an intersection or an overlap. All right, let's see this in practice here. Give me an eraser. Give me an eraser. Now erase with the eraser. That's an idea. Erase with the eraser. Okay, cool. Here we go. Now, to begin solving these things, you want to look at each one separately. So I just kind of put a line down there. And you solve this in the usual way. You say, how do I get the x term by itself? I add 5 to both sides. So that's going to be 3x less than 18. Now what do? I divide both sides by 3. 18 divided by 3 is 6. There we go. X is less than 6. And if I were to make a map of that on a number line, the 6 is, somewhere in the middle. It's an open circle because it says strictly less than 6, not equal. And less than means all numbers smaller, which are over here. So that's -infinity there. That's +infinity there. Okay, that maps out all the solutions to that one. Let's do this other one. So trying to get the x term by itself, I want to first subtract 1 on both sides. So 15 minus 1 is 14. Now you do the old divide both sides by 7 trick. I haven't divided by a negative. I don't have to flip anything around or nothing like that. Okay, now I make a number line. And I'll make my map here. Greater than 2. And it's a strict greater than, so open circle again. 2 is somewhere in the middle. Things that are bigger are on this side, right? Okay. Now, I have two separate solutions here. And the question is, where do they overlap? Where do these solution sets, these sets of numbers, where do they overlap? And the easiest way to see that is to, what I could probably do is something like this. Take this and kind of move it right underneath so that I'm overlapping the number lines. You can kind of see they're going to overlap between 2 and 6. I think what I'll do instead is I'll just say, pretend I drew it all on the same number line. So, or maybe not the same number line, but there's the number line from negative infinity to positive infinity. So this one says everything from 6 going that way. In fact, I think I'm going to try to be everything from 6 going this way. The other one says everything from 2 but going the other way. So I'm trying to sort of draw one number line lined up with the other one. And then you say, oh, here's the overlap. They overlap here. They overlap from 2 to 6. Notice you can't count 2 because 2 is not part of the top. And you can't count 6 because 6 is not part of the bottom. But everything else between 2 and 6 you can use. And so that's why I'm using round parentheses, because we do not include the endpoints 2 and 6. But everything else between 2 and 6 we use. And that is the solution to this system. Okay? When is both this and this? When are they both satisfied? They are both satisfied for numbers that are between 2 and 6. Not counting 2 and 6, but between 2 and 6. And it can be a little bit fun to check it, right? So you're saying if I take something that's less than 2, something like a 0, that it won't work? Well, if I put a 0 here, I'll have 0 minus 5, which is negative 5. That's less than 13. That solves this one. If I put a 0 here, though, I'll have 1 greater than 15. It does not solve this one. Because it does not solve both, 0 does not count as one of our solutions to the system considered together. You're saying something in between 2 and 6, like a 4. You're saying a 4 would work? A 4 would solve both of these? Well, if I put a 4 here, I have 12 minus 5, which is 7. That's less than 13. If I put a 4 over here, I'll have a 28 plus 1 is 29. That's greater than 15. Notice 4 does work for both of them. And then we're also saying that something bigger than 6, I don't know, let's try a 10. 10 is not supposed to work for both of them. If I put a 10 here, I've got a 30, take away 5, which is definitely not less than 13. The 10 will work for this one, but it's not working for this one. So that's what we mean by intersection. That's why we mean by a compound inequalities when they're joined with the word and. That's exactly what we mean. So let's do this one. Here's another one. I think I'll get this arrow out of the way so it doesn't block me too much here. So looking at the one on the left, do this one first. Oh, this one's not going to be too bad. You just divide both sides by 4. Boom. Thinking in terms of a number line, well, you know what? I don't think I'm going to draw separate number lines. I'll just draw one big old number line. Starts at negative infinity, goes to positive infinity. The numbers that are, let's see, that says less than or equal to 5. So I'm going to put my 5 here. These are all the numbers less than or equal to 5. And maybe I'll label the 5 right there. Okay, now let's solve the one on the right. So this says, well, let's see, I'm going to have to subtract 8 from both sides, right? Do that first. And I'll have a negative 2x is less than a 4. Then I have to divide both sides by a negative, ding, 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 ding. And so that means that I have to take this less than and flip it around this way to a greater than. So x is greater than a negative 2. So negative 2 is over here somewhere, right? This is a strictly greater than open circle, and it's greater means to the right, all of these numbers over here. And it's time to form our overlap. Where do these sets overlap? Well, they overlap from negative 2 to 5. Do I include negative 2? No, because negative 2 is not in the orange set. Do I include 5? Yes, because 5 is in both sets. Square brackets. There she blows. Hey, you want to pause for a minute and try this one yourself? Try that one yourself. Okay, you back? All right, let's see. First, you consider each one separately. So this is a little more fancy looking, but again, you solve it just like linear equations. There's only the one thing to watch out for, and that's if you multiply or divide both sides by something negative. That's the only thing that's different. Otherwise, you can do the same old, gee, I feel like subtracting 2x on both sides. Woohoo! So the 3x minus the 2x is an x. And over here, I got just a 5 now. Now I'll do the old subtract 7 on both sides. So I've got x less than negative 2. There's that one. X less than negative 2. Cool. Let's draw that. So negative 2 is just, over here somewhere. And less than means don't include it. So open circle, everything to the left. Okay, cool. Now let's go look at the other one. Oh, we can FOIL, huh? Okay, 16 minus 24x is less than 12x. Cool, cool, cool. I'd like to have all my x terms on the left, so I'm going to subtract 12x on both sides. So I got a 16 minus a 36x, and over here I've now got a 0. Let's subtract 16 on both sides. So in 0 take away 16 is this now. And here's the part where we divide both sides by a negative. So dividing both sides by negative 36 means this has to turn around and become this. Okay, very important. I'm dividing by a negative, so I have to switch that around. So negative, let's emphasize this, I guess. These cancel, of course, but this has to switch around, which is why I switched it over here. On the right side, I got a negative divided by a negative is a positive. A 16 divided by a 36, I should cancel 4s and get a 4/9. Always reduce your fractions. Please, please, please. So 16 and 36 can both be divided by 4. So you just do it. 4/9. So now we take this solution, x greater than 4/9. Well, where's 4/9? Well, that's negative 2. 4/9 is positive. It's over here somewhere. Now this is another one of those strict inequalities. So it's an open circle. Everything to the right of 4/9. Okay, cool. Now it's time to overlap. Where do these overlap? There is no overlap. Well, the solution is supposed to be where they overlap. But they don't overlap. Well, if they don't overlap, there's no solution. So every now and then you'll get a system, a compound inequality like this it doesn't have a solution. There's no overlap, no solution. If you want to if you don't want to write out the whole thing, no solution, you can use this little symbol. That is an actual circle. It's not an O, it's not a 0. It's a circle with a slash through it, and it means empty set. That's the way you actually would pronounce that, empty set. Or you could say no solution too. Okay, so that's cool. That's cool. Those are our compound inequalities where we're considering two together, intersections or the word and. The other major type is unions. And you can tell it's a union because they'll use the word or. It's when you want one or the other. You don't care which one. You don't care which one. Any of them. I think of it this way. You gather together all the solutions that come from either, just like if you were building a collection of Pokemon cards. Anytime you see a new card that you don't have yet, you grab it. You save it. You put it in your collection. Okay, so I'll show you how this works here. Let's solve this one. Got some distributing to do. 7x minus 35 is less than or equal to 14. If I add 35 to both sides, 35 and 14 is going to be a 49. If I divide both sides by 7, that's looking like this. Okay, I'm going to start drawing a number line right now. Less than or equal to 7. Well, 7's over here someplace. It says less than or equal, so it's nice and solid, actually. I'm going to draw it a little bit off so it's easier to see. Less than or equal to 7 means this stuff, all that stuff going that way. Okay, now let's solve the other one. Subtract 5 on both sides, and you say, oh, x is less than 5. Okay, so I should have written my 7 over here. And now I need to find 5 on the number line. That's going to be over here somewhere. Less than, strictly less than, means go this way with an open circle there, right? Okay. Now, remember, this time we're not looking for an overlap. Overlap is the intersection. That's when you're using the word and. It's when you want numbers that solve both simultaneously. That's not what we're looking for here. We have an or situation. We're looking for anything that is in either set will work for us. Anything like, I wouldn't just want to take these, Because look at all these Pokemon cards I'd be throwing away. I don't want to throw away any Pokemon cards at all. So what's my solution then? This is my solution. That's actually my solution. This set of cards already has all of these in there, so I don't get anything new by looking at those. But if I had first grabbed this, let's say I opened up this pack of cards and I got all of those, and then I opened up this pack of cards, I'd say, oh, look, I got some more cards right here, yay! And I'd add those to my collection. So you're taking everything you can get. Every single card you can get is a good one. And so what's the solution to this system? You go all the way from negative infinity up to and including 7. Okay, so notice it's a very different idea than an overlap. It's not overlap. It's take everything you can get. It's greed. I don't know what it is. It's trying to build a Pokemon collection. That's what it is. Which is not greed, but whatever. Okay, let's do this one. Again, the word or tells you that you're building a Pokemon set. Build both sides by 2. Build both sides. Divide both sides by 2. X is greater than 9. Where's that? All numbers greater than 9. Strictly greater than. Open circle, go to the right, greater than. Okay, that's where 9 is. Okay. Now this one. Divide both sides by 2. Okay, I didn't divide by a negative, so I don't have to switch anything around. So x is less than negative 9. Negative 9? That's over here. That's over here. So negative 9 is over here. And again, with the strict inequality, don't include the endpoint. Those. Now, if we were looking for the overlap, we'd say no solution, right? But we're not looking for the overlap. We're looking for everything we can get. So just, again, imagine yourself. You just opened up this set of Pokemon cards and you said, hey, look at all these cards I got. And then you open up this set of Pokemon cards and you say, wow, now I got all these cards too. Okay, it's about having a nice big set. You've got all of these. All of these count. How do you write this in interval notation? Well, you got 2 parts to it. So you have to say, well, you know, this by the way, it goes from negative infinity to infinity, right? So this interval here, reading left to right, you're going from negative infinity to negative 9. Don't include the negative 9. You can't include negative infinity. And then this is your glue. It's a union symbol. It's not quite a U. It's glue, though. It's a union symbol. It says glue these 2 things together. So I'm trying to make it look like a nice union symbol. It's almost like a horseshoe or something. But anyway, union symbol. So you just use a union symbol as glue. And then you say, okay, and then on the other side, go from 9 to positive infinity. So that's how you write a 2-part solution. Using that union symbol is the trick. Okay. And what do we got here? Hey, you might want to pause and try this one too. You want to try this one yourself? Pause. Come back. Okay. So the first thing you do, of course, is you just consider each of these things separately. So just looking over here, I got some distributing to do. 2x minus 6 is less than or equal to 6. I'm going to add 6 to both sides. 2x is less than or equal to 12. I'm going to divide both sides by 2. X is less than or equal to 6. Okay, cool. So on the number line, where are all these? Well, 6 is like over here somewhere. And it says less than or equal to. So this is a solid dot. And it's everything to the left. Okay, cool. Now, let's look at this other one. Distributing again. 3x plus 6 is greater than 5. Okay, cool. Subtract 6 on both sides. 5 minus 6 is a negative 1. Okay, a negative is shown up, but I don't have to switch anything because I did not divide by a negative, and I'm not dividing by a negative now either. I'm dividing by a positive 3, so that I never had to switch the symbol there. It's only if you divide by a negative or multiply by a negative on both sides, then you switch. Never any other time, just only that. Anyway, greater than negative 1/3, so where's that? Negative 1/3, well, if 6 is over here, negative 1/3 is over here someplace, right? Greater than, it's a strict greater than, so it's an open circle. Take all of these. Now, it's a Pokemon collection, right? So you're asking yourself, okay, I open up this set, I get all these Pokemon cards, and then I open up this pack and I get all these Pokemon cards. And then you assume that all the Pokemon cards are on the number line somewhere. Notice we've got them all. Catch them all. We caught them all. We got all the Pokemons. Yay! We got all the Pokemons. Anyway, we got them all. So what's the solution? The solution is the whole number line. All real numbers. Give me a pen. All real numbers are solutions to this thing. How do you say that with interval notation? You say, well, you can start at negative infinity, or, again, you can't equal negative infinity, so it has to be a round bracket, all the way up to positive infinity. That's how you say all real numbers using interval notation. It's everything from negative infinity going one way to infinity going the other way, and everything in between. It's everything. All the real numbers, all of them. Okay. So it pays now and then to kind of look back and say, well, what have we been doing so far? Well, we did the ands, and look what happened, and we had this funny situation with no solution because there was no overlap. And then we had the unions, which is different. It's building Pokemons. We had this special situation with the union and the all reals, and cool, right? Okay, one more. I believe there's one more page. Yeah, one more page, two more examples. I separated these out because they kind of feel a little different to me than what we've been doing. They're not actually different. These count as, how should I say this? These are, these count as intersections, or the and ones. It's just that it's written a little differently. But this is saying that 2x plus 5 is less than 12, and 2x plus 5 is, reading it this way, it's greater than negative 4. So it's a compound statement. It's saying two things at once. It's saying 2x plus 5 is both greater than negative 4 and less than 12. But you got to admit, this is kind of a nice way to write it. So again, always left to right. You want to have the small number over here and the big number over here, and this way. Okay, that's the proper way to write these things. But anyway, we don't really have to be thinking in terms of, hey, is it a Pokemon set? What is it? We don't have to think about any of that stuff, because you can solve these just like you solve equations that have three sides to them. It's just like a three-sided equation. So it's like, focus on this part in the middle here and say, what would I do if I was solving for x? Well, first I'd subtract 5. Okay, subtract 5. Subtract 5 here and here, but also over here, because it's like your equation or inequality now has three sides to it. So if you do a minus 5 in the middle, you have to do a minus 5 on the right and on the left. Minus 4 minus 5 is a negative 9. This is a 2x. This is a 7. Cool. Now, divide everything by 2. I want to divide by 2 in the middle to get the x by itself to cancel the 2 off. So I ought to do it on the right, and I also have to do it on the left. So what have I got? I've got a negative 9 halves here, x, 7 halves. And that's it. I'm done. Wasn't that fun? So these are fun. Interval notation, you would say, well, on reading left to right, you go from negative 9 halves up to 7 halves, and you don't include either because these are strict inequalities. Since you don't include either endpoint, you're using round parentheses on both sides. And that's really all there is to these. Okay, it's like an equation that has three sides, kind of, sort of. One more. We should end with one that's a little bit fancy. This would be a real good one for you to try yourself, actually, to pause and try yourself. And the reason I say that is watching is too passive for anything to stick. If all you do is watch, maybe 5% is going to stick. You'll just say, yeah, I got a rough idea what was going on, sure. It helps if you sing along, like, Big Bird. If you sing along, it'll stick a little better, but I don't think I'm going to sing this one, so no. If you work it yourself, if you encounter the problem yourself and you come across little things and you go, oh, I wasn't expecting this. What do I do in this? Oh, I do this. If you encounter it, if you play with it yourself, then you're going to get anywhere from 50% to 100% it's going to stick. Depending how new it is. If it's brand new, you might only get a 50% stick. Means you have to do it a couple times. If you say, oh, yeah, I so get this. it might stick 100%. But watching me, it's not going to stick. Okay. Pause. Rewind. Okay. What are we going to do here? Looking in the middle, I got to get the x by itself. What don't I like about what I'm seeing in the middle? Well, I really don't like having a fraction. I don't like having that 3 there. How can I get rid of the 3? Well, to cancel the 3, I would want to basically multiply by a 3 up here so that the 3 would cancel. So I'm going to multiply everything by 3. I'm going to multiply the left by 3. I'm going to multiply this thing in the middle by 3. And remember, 3 is like 3 over 1. So you can write it that way. And I'm going to multiply this 20 by 3. So whatever you do to one side, you do to all 3, so to speak. So what do I got? I got a 15 less than, and again, this is cross cancellation stuff happening here. Now I have a 7 minus x and a 60. Cool. That looks a little better. At least there's no fractions. Now keep your eye on the x, and you say, well, the first thing is I really don't want that 7 there. So I'm going to have to subtract 7 in the middle, on the left, on the right. Now what I got? 15 minus 7 is an 8. 7 minus 7 goes away. Now don't forget that's a negative x. 60 minus 7 is a 53, right? That's what I got before. Huh, I did it wrong before. I'm doing it right this time, though. Good. So, okay. Now we got a slight problem here. That's not x yet. That's negative x. So what are we going to do now? Well, what we're going to do now is you could either say multiply or divide. It doesn't matter. I think people are mostly in the habit of dividing. So I'm going to divide by negative 1 everywhere. And because I'm dividing by a negative, flag on the play, because I'm dividing by a negative, those have to switch around. So this will be a negative 8, but that switches around. This will become a positive x, but that switches around. This will become a negative 53. Okay. Now here's the other thing. This is not left to right. I was saying before, you've got to go left to right. Negative 53 is on the left. Negative 8 is on the right. X is in the middle. So that means I have to sort of read this backwards. So negative 53, now look at this symbol coming into the x, right? That's going to look like this. Do you see how that's like a mirror reflection? You might just think in terms of, well, it's pointing at the negative 53, and it still has to point at the negative 53. However you do it. Ooh, I didn't want to do all that. Okay. So it goes like this. And then, again, continuing to read backwards, here's the x. And then there's the negative 8. Notice the thing's pointing at the x, not the negative 8. So over here, it's pointing at the x, not the negative 8. Okay. That's pretty good. That's kind of my solution there. So if you ever get to a point like this where everything's backwards, flip it around. It should always be less thans, always less thans or less than equals. Always, always, and it should always go left to right along the number line, from small to big along the number line. Always, always, always. Otherwise, there's a problem. Okay. So to finish this off, let's put it in interval notation. It's saying everything that goes from negative 53 up to negative 8. Wait, I want green. From negative 53 up to negative 8. Do we include negative 53? Yes, it says it right there. Include the negative 53. Do we include the negative 8? No, because it's a strict inequality. So round parentheses on the right, square bracket on the left, and we are done. So, does that mean you're ready for the homework? Well, you might be. You might be. Usually myself, what I like to do is after I've gone through a video or a lecture or read a book or whatever, usually what I like to do is I like to go back over my notes first before I hit the homework and sort of review to myself, okay, what just happened? What are all the key pieces? What are the key things I need to remember? Most likely I'm going to write this on some piece of paper somewhere. These are the key points. This is the key stuff I have to remember. I make myself a nice little note to my future self in case I ever need this stuff again. And then I use that piece of paper to test myself doing the homework, to say, hey, let's see if I can do the homework here. Because when you're doing the homework, you're not going to quite remember. You're going to want to look back, right? Try looking back to your note sheet to see if your note sheet helps. And if your note sheet doesn't help, guess what? You can improve your note sheet. You can say, oh, wait, there's also this thing to worry about, or so on. This is extremely valuable, especially in classes that have like midterms and final exams. So I just thought I'd point that out, just give you an idea. But it will be time for the homework soon. How do you turn this thing off?